Please don't mix and match. So, we had a 4 kilogram mass going to the right at 6 meters per second, and it's going to collide head on with a 10 kilogram mass heading to the left initially at 1 meter per second. This is a one-dimensional, perfectly elastic collision, PEC. I know two things are true. Momentum is conserved because it's a closed system. I have only these two objects. There is no planet, not worrying about weight. The other thing I know is true is that kinetic energy is conserved because I told you it's a perfectly elastic collision automatically. That means kinetic energy is conserved. So I know my initial momentum equals my final momentum. So this was 14, which we've done many times before, is equal to 4 times V A final plus 10 times V 10 final. Let's try that again. 4 times V 4 final and 10 times V 10 final. Now I didn't write the vector symbols over the velocities. It is a one-dimensional problem. If my velocity ends up being positive, it's in the positive direction, negative, it's in the negative direction. Because there's going to be a whole lot of writing here in this first technique especially, I'm trying to simplify how much I have to write on the board. I'm going to make another simplification in a moment, but I at least want to set up the problem, set up the equations. So this is my conservation of momentum problem equation. Total initial equals this total final. Any questions how I got this? All right, I know kinetic energy initial equals kinetic energy final. Well, we've done the initial, that's 77. And that's going to be equal to 1/2 times 4 times V 4 final squared plus 1/2 times 10 times V 10 final squared. And this is where it's convenient that if V4F or V10F happen to be negative, when I square it, that's going to go away, so we're not going to run into an issue there. Questions about where my kinetic energy conservation comes from, where this equation comes from, or for the purist, from where this equation comes. All right. I have two equations, two unknowns. This is solvable mathematically as long as they are independent, which they are. Here's the next conceit that I do in order to be able to simplify my writing. I hate writing subscripts. At some point, I'm going to miswrite it. And so what I'm going to do is I'm going to establish, I'm going to say C. Actually, why don't I use E and I just need 2 letters. I'm going to stick with what I usually do. C is V4F and D is V10F. That's not a Descartes, that's just the letter D. It is a local definition for this problem. And so my equations become 14 is equal to 4C plus 10D, and 77 is equal to 2C squared plus 5D squared. To me, it just looks like a whole lot simpler. All right, so how do I solve? We've got 2 equations, 2 unknowns. What do I do? We typically solve 2 equations, 2 unknowns.
would do is I would go ahead and square the 2C and the 5D. So I can get the 4C. That way I can cancel those two
Oh,
out.
wait, so you said square this equation?
Yes.
Yeah, then we end up with an equation with an expression which has a C and a D in it, when I square the side. That's not gonna be the simplest way. Because only the C is squared, only the D is squared, the 2 and 5 are not squared.
Oh, okay.
Yeah, the 2 comes from this 1/2 times 4, and the 5 comes from the 1/2 times 10. All right, so how do we solve it? What can we do?
Substitution, like set one of them to be equal to one of the terms and then put it into the other equation.
That sounds good. So let's solve for C. So I know that 4C is equal to 14 minus 10D. And so C is equal to 3.5 minus 2.5D. I did that right. So 14 divided by 2 is 7, divided by 2 is 3.5, 5, okay. I'm feeling decent enough about that. Plug that into the second equation. So we have, we can go for spectacular visual effects here with different color. 77 is equal to 2 times 3.5 minus 2.5D squared plus 5D squared. So basically took that, popped it into here. Now the reason I solved for C instead of solving for D in the first equation is just that was the smallest coefficient that for some reason, the deep psychological scars from my childhood, I just wanted these numbers to be bigger than 1. No special reason other than that. So this becomes 77 is equal to 2 times that thing squared plus 5D squared. All right, reminder, A minus B squared is equal to A squared minus 2AB plus B squared. So 7/2, so 49/4. So 12.25 minus 7/2 and 5/2, that's 35/4 times 2. 35/2, so 17.5 plus 6.25D squared plus 5D squared. Now, it'd be helpful if someone's checked this, but if it's wrong, I'll know at the end. This should read into 2. And I have a quadratic. So let's get everything over to the right side. So that's 17.5D squared. Oop, I lost, that should be a D in there, I lost my D. Minus 35D minus 4.5, that would be 5 to 52.5. And conveniently, 17.5 goes into all those numbers. So I'm left with d squared minus 2d minus 3 equals 0. Doesn't always work that way. So how do we solve that? Okay, that'll always work. And so d is equal to 2 plus or minus the square root of 4 minus 4 times 1 times negative 3 over 2. So this is 2 plus or minus the square root of 16 over 2, which is 2 plus or minus 4 over 2, which is, if we add, we get 3, or if we subtract, we get negative 1. So I know we've done something right, because I was expecting one of those numbers. And if I looked at the solution, I would have expected the other one. Let's figure out what the value for C is. That's the velocity of the 10 kilogram mass, that was D. Let's find out the final velocity of the 4 kilogram mass. So D is equal to 3. Give myself some room over here, because I think I'm off camera at that point. So we have two values for D. We have we have positive 3, that's meters per second, and then 1 meter per second, negative 1 meter per second. I know that C is equal to 3.5 minus 2.5 times D. Written right there. And so when D is equal to 3, C equals 3.5 minus 2.5 times 3, which is negative 4 meters per second. And if that's my value for D, we get 3.5, C is 3.5 minus 2.5 times negative 1, which is 6 meters per second. So I have two solutions, one of which is the actual correct answer, one of which is not. What is the correct answer, or which is not the correct answer, and why? And I guess a vague hint is that one of the answer that is not the correct answer to this problem, I knew we were going to get. Think through the scenarios. So we got the 4 coming in like this, and the 10 coming in like that. They collide. If this is the solution, what does the 10 kilogram mass do after the collision?
It keeps going to the left.
Why?
Because it's a negative.
Don't forget, that's C there. That's the 4 kilograms.
C. Oh.
That's the 10 kilogram.
Okay.
So therefore, you're along that line of thinking of what happens to the 10 kilogram?
The 10 kilogram, it would end up going to the right side.
All right, and the 4 kilogram?
It would end up going to the left, so they would divert.
Okay, so they're heading towards each other like this, and then they bounce off. That is this solution. What about this solution? What's happening here?
they don't collide, cause it has the same, velocity.
Yep. Because mathematically, all we said is I want some value for these two things so that my momentum stays the same and my kinetic energy stays the same. Well, if they never touch each other, that stays the same. So the advantage of this technique is that you get confirmation at this point about whether you've done something right or not. Because one of your solutions should be what you started with. This is not the correct answer to the problem because the problem said a collision. And no collision is taking place here. So after the collision, the 10 kilogram is bouncing backwards at 3 meters per second. And the 4 kilogram mass has bounced backwards, that's 1 meter per second. This is after. So the advantage is you should have the solution of they never touched each other, and so you have confirmation of something's gone right. The disadvantage is you're dealing with a quadratic. And by the way, this particular answer could also have been factored. This would be d minus 3 times d plus 1 equals 0. And so if that product is equal to 0, that means d minus 3 equals 0, or d plus 1 equals 0, and that works if d equals 3, or if d equals -1. Usually it doesn't factor out that nicely, but this particular problem, I picked these numbers so that things would work out well. All right, questions about this technique before we do technique number 2? All right, technique number 2, we're going to start out basically similar to what we did before, except the fact that I am going to use more generic terms here. We're going to derive an equation. So I've got mass 1 moving at some initial velocity of a. I have mass 2 traveling at some initial velocity of b. This is before. Afterwards, mass 1 is traveling at some final velocity of c, and mass 2 is traveling at some final velocity of d. This is why I chose C and D before, is because of this. Momentum is conserved, and so I know that M1A plus M2B, that's mass times velocity of the first one plus the second one, is M1C plus M2D. Final momentum of the first one plus final momentum of the second one. Kinetic energy is conserved, and so we've just got 1/2 M1 times A squared plus 1/2 M2 times B squared is equal to 1/2 M1 times C squared plus 1/2 M2 times D squared. It's exactly what we did over there, except I used real numbers over there instead of just letters, but it's the same process. 1/2 mv squared, mass times velocity here. I'm now going to take these equations and I'm going to get the common masses all on one side. So I'm going to get all the M1s on the left and all the M2s on the right. So I have M1A minus M1C equals, then M2 is over on the right hand side, M2D minus M2B. So I'm just switching sides, and since there are terms I'm doing, I add or subtract. So that's just going over there, and this is going over here. I'm going to do the exact same thing for the kinetic energy equation. I'm going to take my M1 side, bring my M1s over here, and bring my M2 over to the right. And I'm gonna multiply by 2, just get rid of the 1/2. So this becomes m1a squared minus m1c squared is equal to m2d squared minus m2b squared. I'm now gonna factor. I have two terms here. What is the common factor? More specifically?
M1.
Yeah. So I'm gonna factor that out, so I got M1, I'm left with A minus C, is equal to M2 times D minus B. That's just that one. I'm gonna do the exact same process for the one right above it. This becomes M1 times A squared minus C squared equals M2 times D squared minus B squared. And so now I have a difference of perfect squares. Do this little side note over here. A squared minus C squared. How does that factor? They not teach factoring anymore? So, I realize some people are writing down, but over here, when I took this d squared minus 2d minus 3 equals 0, and then I factored it into this. Which of you look at that and go, I have no idea what you just did there? Or is this familiar to you? I'm not saying that you can do it in your sleep, but this is factoring the trinomial.
Say again, I'm sorry, I was writing.
Okay. Good, sorry, I did that prematurely. All right, so when I went from here to here, and I factored it, I'm trying to figure out whether this is something that you have seen before or something that is not taught anymore. And I'm getting absolutely no sense one way or the other right now.
I've seen it before.
Okay. Got a couple other nods here. I'm not seeing anyone shaking their head. All right. So factoring over here. I'm hoping somebody who's seen it before can tell me how to factor this. I assume the expression FOIL is still used? Okay, got some nods on that one. All right, spoiler alert, this is A minus C, A plus C. So if I FOIL, I multiply the first ones together, I get A squared, outer, plus A times C, inner, minus A times C, last, minus C squared. Those cancel out, and I'm left with A squared minus C squared. So this right here, I have a difference of perfect squares, will factor very nicely, and I'm left with M1 A minus C times A plus C equals M2 times D minus B times D plus B. So all of these go together, and that top one becomes this one right here. I did it in that order for a particular reason, because it's about to save me a step. I'm now going to divide. I'm going to divide the left-hand side of the kinetic energy equation by the one we got from the momentum equation. Now the math people tell me as long as I divide by equal things, I'm good. So I'm going to divide the right-hand side by this part that we got from the momentum equation, because they're equal to each other, so dividing both sides by it, by each one, is legitimate. And so my mass ones cancel out, A minus C cancels out, my mass twos cancel out, and D minus B cancels out, and what I'm left with is A plus C is equal to D plus B. Or more traditionally written, A minus B is equal to D minus C. A minus B, that is the relative speed of approach. So from B's point of view, how fast is A coming at it? Or is mass one coming at it? In our particular problem, this was 6 minus -1. So from B's point of view, or from the 10 kilograms point of view, the 4 kilogram mass is coming at it at 7 meters per second. And that's equal to the relative speed of recession. So the speed of approach, the relative speed of approach equals the relative speed of recession. So if from mass two's point of view, mass one's coming at it at 7 meters per second. After the collision, from mass one's point of view, mass two's going away at 7 meters per second. That's what this is telling us. And so when I plug into my equations, I got my momentum equation right here, that stays. But now I have a second equation of 7 is equal to D minus C. I have two equations, two unknowns still, but I don't have to deal with a quadratic. At this point, so many different techniques to use. Substitution, why not? So D is equal to 7 plus C. So plug that into here. So I have 14 is equal to 4 times C plus 10 times 7 plus C. So 14 is equal to 4C plus 70 plus 10C. Subtract 70 from both sides, and I get negative 56 equals 14C. C equals, I hope, negative 4 meters per second. And then plug it in here. D is equal to 7 plus negative 4, which is 3 meters per second. Hey, and that's the same answer we had last time. So technique number 2, you solve the momentum equation, but you've got this relative speed of approach equals relative speed of recession. So that was going this way at negative, to the left at 4 meters per second. Questions about technique number 2?
Each time you do it, do you have to derive the equation, or is
No.
it always gonna be?
You can jump straight to that.
Okay.
Yeah, if you had to derive the equation, there would be no advantage whatsoever, except for the people who just love doing derivations. And I probably mentioned this before, I tutored the young man years ago who, whenever needed to solve a quadratic, would always complete the square. Never use the quadratic equation or the quadratic formula. In essence, he was deriving the quadratic equation every single time. But that's the way his mind was working at that moment, so it's legitimate math. Okay. Other questions about this? The third technique is the one that I usually use. The advantage is that once you get used to it, in my opinion, it's a whole lot faster. The disadvantage is it's slightly more abstract. So we started out with this, it was the 4 kilogram mass going at 6 meters per second?
Yep.
And the 10 kilogram mass going backwards at 1 meter per second. So my momentum of the 4, momentum of the 10, and total initial momentum. So this was 24, this was negative 10, and that was 14. This is what I refer to, I generally call it the lab frame, but it's actually the problem frame. Problem frame, and parenthetically I'm going to call it lab frame because that's often what I call it. In essence, you're standing on the sideline, you're watching this thing go. From your point of view, that thing's going at 6 meters per second, the other one's going at 1 meter per second, they collide, and we have answers from the person who's standing by looking at this problem. However, we don't have to be in that frame. We can observe. Suppose, for example, you have this problem going on and you're moving at 6 meters per second also. So you're watching this thing as it's unfolding. If you're traveling 6 meters per second to the right, how fast will this one look like it's going?
0.
Right. So if I'm in the 6 meter per second reference frame, let's write down reference frame. This one looks like it's not moving. The other one looks like it's coming at me at 7 meters per second. What would you put in velocity here? Velocity 4, velocity 10. So this would be 6 and negative 1. So now this is 0 and this is negative 7. And so the momentum in that frame, if I'm cruising along just paralleling this 4, so the 10's coming at me at negative 7 meters per second, its momentum is negative 70. And so my total momentum is negative 70 kilogram meters per second. So I can change the amount of the total momentum just by changing how I'm looking at it. If instead I'm moving backwards at 1 meter per second,